Today we will discuss about Gauss's law. Gauss's law. This law gives a relation between the net flux through a closed surface and the charge enclosed by the surface. According to this law, the net electric flux through any closed surface is equal to the net charge inside the surface divided by epsilon naught. That is, phi equals to integration closed integration E vector dot dA vector equals to Q enclosed by epsilon naught. Q in means Q enclosed by the surface. This implies integration E dA cos theta equal to Q in by epsilon naught. If theta equal to 0 degree, then E into integration of dA equals to Q in by epsilon naught, or EA equals to Q in by epsilon naught. This is equation 2, where Q in is the total charge enclosed by the closed surface, and E is the electric field at the surface due to all charge inside and outside. For example, here given there are some this is a closed surface which is enclosing charge q1, q2, minus q4, q5, minus q3, etc. And there are also charges in outside this surface, that is q7 and plus q6. So from the Gauss's law, flux of electric field will be equal to Q enclosed by the epsilon naught, because here enclosed charge is q1, q2, minus q4, minus q3 and plus q5. So net charge here we can write q1 plus q2 plus q5 minus q3 minus q4 divided by epsilon naught. For example, you can, here it is a enclosed surface is shown and a q charge is placed inside the enclosed surface at any point. Now if we want to calculate the electric field due to this charge, then we can use the Gauss's law. For example, first we calculate the flux. So we choose a elementary area at this point, and it's that is the direction of area is in this direction at this point, because area vector is always normal to the surface, and electric field is along this line, because electric field due to point charge always in radial direction. So flux will be from the formula phi equal to integration of E vector dot dA vector close integration, or integration E dA cos theta equals to Q in by epsilon naught. Now phi equals to integration E dA cos theta equal to Q by epsilon naught, because only one charge is closed by this surface. Gauss's law is valid for the electric field of any system of charge or continuous distribution of charge. In practice, however, the technique is useful for calculating the electric field only in situations where the degree of symmetry is high. It is used to evaluate the electric field for charge distribution that have spherical, cylindrical or planar symmetry. Here we will see a example of application of Gauss's law. Here a charge enclosed by a spherical surface, and we have to find the electric field due to this charge. Then we can use the Gauss's law to find the electric field. Now electric field due to a point charge, consider a Gaussian sphere of radius r. According to Gauss's law, phi equal to Q in by epsilon naught. So integration E vector dot dA vector Q in by epsilon naught integration E dA cos 0, because electric field and area vector is in same direction, so theta equal to 0. So cos 0 is equal to 1 Q by epsilon naught, because Q in is Q, or E, this implies E into integration of dA Q by epsilon naught, or E into integration of dA, that is total area 4. So total area of a sphere is 4 pi r square. So E into 4 pi r square equal to Q by epsilon naught. Hence E equals to 1 by 4 pi epsilon naught q by r square. Thus, using the Gauss's law, we have calculated the electric field due to point charge at a distance r from the charge. Now, we should know one important topic, that is plane angle and solid angle. This is a triangle, and we see that this is called angle, that is the meeting point of two non-parallel line where it meets. Then the figure made by this is called angle. Here this is the angle theta, and if theta is very small, then we can write theta equals to L by R, where L is the arc AB and R is the distance of AB from this point O. So theta equal to AB by O, or AB by OB. Again, if we have not figure like this, and consider we have a figure like OACBO, then again we can calculate the angle, and theta is very small, so we have take this length, draw a perpendicular on OC, and it is a AB. So but we know that the AB, we know that L, and this angle alpha. So in triangle ABC, cos alpha will be equal to AB by AC AB by BC, sorry, AB by BC, not AC. AB by BC. So AB by L, this imply, hence AB will be L cos alpha. So we know that theta is divided L by R, means arc length divided by distance. So arc length is here AB. So theta equal to AB by OA or AB by OB equals to, now the value of AB is L cos alpha. So this will be L cos alpha by R. Again, another concept is similar to the plane angle. We also know about the solid angle, that is the angle made by a cone by a surface at any point is called solid angle. For example, it is a surface, and if we take any point at here, then surrounding this point and this circumference, the line surrounding this point and this circumference of this area, and joining this circumference and the line from this point to this circumference, then this the figure drawn here, this will be called as solid angle. So the solid angle is made by surface, and this distance are R, and it is represented by omega. For a small angle we are using d omega. So symbol for solid angle is omega. Both are read as omega. You can use also this symbol or this symbol, or d omega, ds by r square. It is defined mathematically, that is area divided by r square, where r is the distance of area from the point. So we have written ds by r square. Now if the area is not like this, that is not the exact in front of the point, but somehow tilted, then we can calculate area, that is this area is given, but this area is not given. Again we can calculate the solid angle. We have to take its component in this direction, and if this angle is theta, then ds in this direction, the component of ds will be ds cos theta, and this distance is r, so we can write d omega equal to ds theta by ds theta by ds cos theta by r square. Unit of plane angle is radian, and unit of solid angle is steradian. and both are without dimension. So there is no dimension of radian and steradian. Again we can write d omega equal to ds by r square, and this is the situation where this length is equal to r and this length is equal to r, and this is making solid angle at this point, this surface. So area of this surface will be r square. So from the definition, d omega equal to ds by r square or r square by r square, and in this case this is called, this solid angle made by this area is called 1 steradian. So this will be 1 steradian. Thus 1 steradian can be defined as the area, the surface whose area is equal to the square of distance from the point, then solid angle made by that surface is called 1 steradian at that point. So this is 1 steradian. Again in plane angle it is also theta equal to L by R. If this is equal to R, that is distance from the point, the arc length is equal to the distance from the point to the arc length, then angle made by this arc length will be equal to 1 radian, that is theta equal to L by R or equals to R by R equal to 1 radian. Now the total plane angle made by the closed loop at inside point is 2 pi radian. The total solid angle made by a closed surface at inside point is 4 pi steradian. Now we should take the proof of Gauss's law. Proof of Gauss's law. Consider a surface. Let a charge q is enclosed by a surface as shown in the figure. Consider an elementary area at a distance r from charge q. It is elementary area at a distance r from the charge q. The angle between electric field and elementary area is theta. That is the angle here, area. This area is in this direction, but electric field is in this direction. Electric field is always in radial direction, so electric field will be in this direction, but area may be in another direction. It depends on the surface which we have chosen. So here the ds direction is in this, that is area vector is in this direction. The ds is the area vector. Hence electric field at elementary area due to charge is equal to 1 by 4 pi epsilon naught q by r square. We know that this formula from earlier. Just electric field at a distance, at a point which is at a distance of r is given by 1 by 4 pi epsilon naught q by r square, magnitude, and direction in along the radial direction if charge is point charge. Now flux of the electric field through elementary area d phi equal to E vector dot ds vector from the formula of flux E ds cos theta. Hence net flux through the whole surface equals to phi integration of d phi or integration of E ds cos theta or integration of, we know the value of E, 1 by 4 pi epsilon naught q by r square and ds into cos theta, or q by 4 pi epsilon naught integration ds cos theta by r square, and q by 4 pi epsilon naught, we know that ds cos theta by r square is the angle, elementary angle made by that area at that point, elementary solid angle made by that area at that point. So we write it as a d omega, to integration of d omega, or equals to cone by q by 4 pi epsilon naught integration d omega, because a closed surface made 4 pi angle, 4 pi solid angle at the at any point inside the surface, so it will be 4 pi. So equals to 4 pi cancel, q by epsilon naught So q enclosed because surface encloses this charge, so we have written here q enclosed by epsilon naught. So phi equals to q enclosed by epsilon naught proved. An electric dipole is placed at the center of a sphere. Find the electric flux passing through the sphere. According to Gauss's law, phi equal to q in by epsilon naught. So plus q plus minus e by epsilon naught equal to 0 by epsilon naught. Hence phi equals to 0. So flux through this surface, closed surface, will be 0 due to dipole. Now, a a point charge q is placed at the center of a cube. What is the flux linked with A, all the faces of the cube, B, each face of the cube, C, if the charge is not at the center, then what will be the answer of part A and B? Solution. According to Gauss's law, phi total equal to q closed by epsilon naught or q by epsilon naught. B, the cube is a symmetrical body with 6 faces and the point charge is at its center. So electric flux linked with each face will be phi each face equal to phi total by 6 or q by 6 epsilon naught answer. Next, if charge is not at the center, the answer of part A will remain same while that of part will change, because in this case symmetrical situation will be violated in the case of B. So the answer of B will be changed. Next question. The electric field in a region is given by E vector equal to alpha x into I cap. Alpha is a constant of proper dimension. Find A, the total flux passing through a cube bounded by the surface x equal to L, x equal to 2L, y is equal to 0, y is equal to L, and z is equal to 0. B, the charge contained inside the above cube. Charge contained inside the above cube. Here electric field is along x direction. So face ABCD and EFGH are perpendicular to electric field, that is theta equal to 180 or 0 degree, while the other 4 faces are parallel to the field. Theta equal to 90 degree or 270 degree. The flux through these 4 faces will be 0. Now phi ABCD, that is flux through surface ABCD, will be E vector dot E vector into A vector. So here given E vector is alpha into L I cap dot into L square into minus of I cap. Since E vector is alpha into X I cap or equal to alpha into L I cap at ABCD, because it is at a distance, here x is equal to L, so we have put in x is equal to L, and A vector is equal to L into minus I cap, because area is at this point is in this direction but the side length is L, so area will be L square minus I cap. So phi ABCD will be minus alpha into LQ. Again phi EFGH equal to E vector dot A vector 2 alpha into 2L. Similarly here x is equal to 2L, because at this face is at a distance of 2L from the point A of Z axis. So alpha into 2l into I cap dot l square into I cap, because at this surface at this surface area vector is in this direction, so area vector will be l square into I cap. So we have written phi EFG is equal to alpha into LQ. Hence phi net equal to phi ABCD plus phi EFGH equals to minus of alpha into LQ plus 2 alpha into LQ, or alpha into LQ. Now according to Gauss's law, phi net is equal to Q enclosed by epsilon naught. Hence Q enclosed equal to phi net epsilon naught, or equals to epsilon naught alpha into LQ. Answer.